Okay, I hope the PPT is visible. So in the previous class, we stopped with learning about the dynamic programming. Okay, so in the previous class, we were discussing about dynamic programming. So basically what we saw is that when you're trying to reconstruct a particular points, there may be some objects which are there in front of the other objects, and because of which not all 3D points may be visible in both the left image as well as the right image. So there may be some points in the left image which may not be visible in the right image and vice versa, and we call such conditions as the occlusions or the disocclusion and occlusion cases. So dynamic programming was a way by which you can detect and remove the occluded cases, and it is basically an optimization algorithm. So what we saw is that we kind of create we write what are the different observations of the or the points which have been observed in the left plane and the right plane, and accordingly we create a grid. And from that grid, what we did was we try to form paths, right, depending upon what is the combination here. So there may be different paths which are formed. What we do is we try to find out which is the optimal path, and how we find out the optimal path is by giving some penalty to those cases where those cases which have been identified as occluded cases or disoccluded cases. And you can see that penalty is similar to saying that it's basically an error, right? So we are going for the path that gives the least penalty, or the path which has the minimum cost to the error. So basically it's a minimization problem where we try to minimize an error function, okay, and we try to find the optimal path which has got the least error or least penalty as possible. So this was what we had discussed in the previous class. Now, what we'll be discussing about is about the smoothness constraint. Okay. Now that is another approach to the binocular fusion technique. So in the smoothness constraint, if you remember, we had been studying about the disparity map, right? That is, if you are given a left image and if you are given a right image, you can calculate the disparity map. So disparity map is nothing but trying to find out what is the difference in the distance between each of the points in the left image and right image. That is, we also saw that if the images are aligned among its epipolar lines, what we see is if we are taking a particular point in an image, okay, and if it is aligned by its epipolar line, then the correspondence point which is corresponding to this particular point in the right image will lie along the same row, okay. So that means if you're trying to find the disparity or the difference between those two pixels in the two images, you see that the disparity will lie only in one or among one of the along one of the coordinate axis. Okay, that means here, since it is the same row, it will be only along the columns that we find this disparity. Okay, so therefore I can write it. I have a point over here, okay, and I consider a small window here. I can write it as, let's say, w1i, where 1 represents the left image. If it is a right image, let's say it's i2, then I write it as w2i plus di, where d represents the disparity. And like that, if I consider several points within among the two images, then I can create a disparity map like this. And we have also seen how what is the effect of the window size in creating the disparity map, right? So let's say you have a disparity map like this. Now when you are trying to impose the smoothness constraint, what we are trying to say is that the disparity map that you have, okay, it should obey the smoothness constraint. That means if you are comparing, or if you are taking a particular neighborhood along a particular pixel or a point, then there should be some smoothness around this point over here. Okay, in the sense there should not be a sudden rise or steep change in the value of the intensity values in the disparity map. Okay, so that is how you can constrain to the smoothness of the particular image. So this technique of where you put this constraint of smoothness, how we achieve it is by using an or by formulating that as an energy minimization problem. So let's say what you can do is you can create or you can build an error function, okay, in terms of the similarity between the two windows as well as imposing the smoothness constraint. That means I can write a formula which says that capital E, which is basically the error function that needs to be minimized in order to achieve smoothness, okay, is equal to alpha, some constant, E data I1, I2, D. So this E data is basically looking at the similarity between the two windows, plus beta, some coefficient that is used to control the smoothness. Okay, and the smoothness error function is given by E smooth D. The corresponding equations for E data, and the equation for E data is given over here. Okay, so as I said earlier, it is a measure of the similarity between the two windows. So I take the first window, second window, take the difference of that, square that, and take the mean, right? So here this sum of squared function, okay, is basically trying to see what is the similarity or the difference between the two patches here, and what we are trying to do is we are trying to minimize this error function, and in order to attain the smoothness constraint. And another term that we have here in the error function is the E smooth, or the error with respect to the disparity map. So here what we are doing is we basically have a formula or a function which is dependent on the difference between the disparity of the particular point that we are considering, okay, minus its neighborhood. Okay, in the sense what we do is we take a particular point, let's say I, okay, if these two are I, then along that same point I take a point here, I look at the neighbors, okay, and I try to find a function which is dependent on the difference. So what I'm doing is I'm trying to see how different, okay, or how less similar, or less smooth this particular pixel is with respect to its neighbors. Okay, so by minimizing this, what I'm trying to say is I'm trying to say that this whole neighborhood over here is a smooth function, okay, or you do not have any sudden changes. But although we are putting the smoothness constraint over here, okay, there are some places where it is not applicable. Like for example, if you have some edges, okay, as you see over here, if you have some edge points where you have a particular object and a particular background, okay, then there is a sudden change in the what to say, the pixel values in the disparity map, right, corresponding values. So here we do not have a control of the smoothness constraint, and we do not want that. Okay, what we are trying to do is trying to smoothen out or reduce the error, okay, with respect to all the other background pixels or all those that belong to the same object. And we can attain, or we can achieve this kind of an energy minimization problem. We can perform that using the graph cuts method. So if we look at the an example of the result of using the smoothness constraint, this is how you get the result. Okay, so in the previous class what we saw was we tried to see how the disparity map can be used to reconstruct this kind of an image, in the sense to see what is the relative depth of various objects from the stereo images. Yeah, and if you remember, there were a lot of blue portions. That means there were a lot of noisy regions. And using or by incorporating the smoothness constraint, we can see that that kind of the noise has reduced a lot in the while you're trying to segment different objects given in a scene. Okay, and an example of an application where you can use the binocular stereo vision is the robot navigation. So the robots, you can fit stereo cameras in the robots, okay, and these stereo cameras can be used to capture images of the left and the right, and from that it is able to detect what is the depth information, okay, basically using the disparity information. It is able to relate, okay, if there is an obstacle present in front of it, and at what distance, what is the relative distance of each of those objects, and so on. Okay, so if you remember the different steps of the reconstruction, what we discussed was in the stereo fusion, right? Or in the stereo image reconstruction, you have a left image and a right image, and basically what you're trying to do is, given a 3D coordinate or a 3D point in the world coordinate, we are trying to reconstruct this particular point, okay, or you're trying to find out this particular point with respect to the left image and the right images alone. And for that kind of a reconstruction, what we assumed is that the camera parameters are known to us. Okay, so once we know the camera parameters, then we can proceed with the epipolar constraint, and we can try to we first find the pixel pair correspondence, okay, that is in the left image given a particular point, okay, how do you find the correspondence point in this image? So for that we need to find the epipolar line, and from that we try to scan and search for the point that matches the best with that of the given point, okay. So like that we establish the pixel to pixel correspondence, and once that is established, what we do is we just project it both the points, and we try to reconstruct what is the 3D point. So that is what we were discussing till now. Now coming to geometric camera calibration, that means when we were learning about this, what we had assumed is that if, let's say, the camera parameters, if you are considering it as PQ, or let's say if it is PP dash, okay, then what we assumed is that these camera parameters were known to us, right? Now, how do you find out the camera parameters? So for that, you can, given a particular camera, okay, you can find or calibrate the camera. You can do some calibration techniques in order to find out those camera parameters, that is the intrinsic and extrinsic parameters of the camera. So how we find out that is, we can make use of the calibration rig for that, okay. So let's say you have a camera over here, right, and what you can do is in order to calibrate the camera, okay, that is in order to find out the parameters of the camera, what we can do is let's say we are arranging a grid over here, okay, in all the three directions. That means three planes. We are arranging three planes, right? And this particular intersection of all those three planes, we consider that as the origin of the 3D world coordinate. Okay, so given these three frames with a grid-like structure, okay, and given this point of intersection of all those three planes as the point of origin of the world coordinate, okay, and also given the fact that all these three planes are perpendicular to each other, what we do is we assume certain points on this particular grid. So let's say I'm assuming a point over here, I'm assuming another point here, and maybe another point here, okay, or probably another point here, or so on, okay. So and many such points, okay. So what I'm doing is I'm trying to locate, or I'm trying to select certain points along this calibration grid that is given here, okay, in all the three planes. And these points, since it's a grid, we are choosing selecting these points to be the intersection of each of these grids. Now once you have these points which are determined, what is done is an image of this particular system or this particular calibration grid is taken, okay. So once that image is taken, in that image you can try to find out the corresponding. So if these are capital X, which means these are the 3D involved points, then the corresponding 2D points can be calculated. So how that is calculated is, now all that we have is, when you're taking an image, okay, all that you have is all these grids, right? So when an image is taken, you have grids, and since it is three different planes, it's not I'll just draw for the half of it. Okay, let's say you have these grids over here, right? Now, since you have these grids, I can find out these points of intersection, okay, in the particular image. Okay, I can use a corner detector. Let's say something like the Harris corner detector can be used in order to find out all these corners. So once these are found out, I can easily find the correspondence. That is, I can find out which of these points corresponds to which of the points over here. So that is how what we do is we try to relate these capital X to the small x. That means the 3D points which are present in the calibration rig to the 2D points which are obtained in the image. Now, once these two are obtained, okay, we know that you have the projection, if capital P, let's say, represents the camera parameters, then I can say X is equal to the small x, right, is equal to P capital X. That means if X, this capital X is the 3D point, and capital P is basically the camera parameters, then I can say that the small x over here is the image. Okay, and this is basically using the camera projection model, right? So if I know this capital X, okay, from the information that is given over here, or that has been selected, and if I know this small x, that is, if I find the corners and then I know which one corresponds to which, then that means I can find out this capital P. Okay, so this is one way, and capital P is nothing but the camera calibration parameters. So this is one way by which you can try to calibrate the parameter. That means we purposefully we keep a grid-like structure where you have different planes, okay, three different planes perpendicular to each other with a grid-like structure, and within this grid-like structure we select these points of intersection. So once you have these points of intersection, after you take the image, you can use some kind of a corner detection algorithm to find out all the corners, and then we can try to just find the correspondence. Now it becomes easier to find the correspondence between the different points. Now once that is done, then using this, so what I get would be a system of some linear equations, okay, and from that I can find out this capital P. Okay, given there are sufficient number of points over here and I select sufficient number of 3D points, I'll be able to find a very good estimate of this capital P, which is the camera calibration parameters. Now, although theoretically it sounds fine, okay, practically when you have a look at that, finding the exact estimate of the camera parameters, okay, it is nothing but an optimization problem. Okay, so what we do is we first try to find out an estimate of the capital P, and then we will try to project it back to the image. We try to project it back and see how good the values are, and depending on that we keep changing the estimate of the camera parameters in such a way that the back projected images will show proper results. So I'll just explain what that means with the help of a diagram. Okay, so this is regarding the estimation of the parameters. I'll just skip these right now. Now, okay, before I move further, one more point that I need to discuss is when we are considering the different points, okay, we should not consider all the points that lie in the same plane, because see, what we are basically trying to do is we are trying to find out what is the projective transformation between the image, okay, which has been taken by the camera and the actual 3D scene, right? So while the camera is taking the image, what kind of a projective transformation has occurred, okay, to receive or to get that image is what we're trying to calculate. So if you're just looking at some points which are lying along the same plane only, then what happens is the estimate that we are considering for the camera parameters, okay, is not going to be a good estimate. So we need to consider points which are present in different planes, okay, in order to get a good estimate of the camera parameters. Okay, so this is this is one example where we'll see how the camera calibration is formulated as an optimization problem. Okay, so let's say these are the different points that I'm considering. Okay, so this is my calibration grid, and I have some points over here along these two planes. Okay, and I'm taking the image. Let's say I'm taking the image from the camera point of view is somewhere from here. Okay, so if I take an image from here, I might get something which looks like this. So this is basically the image I am. Okay. Now, once I have the image of this, okay, that means here these are the different points, okay, which has been corresponded, or the correspondence points has been obtained over here. Now we know that small x is equal to capital P into X, okay, where you have capital X, which are the 3D points, P is the camera parameters, and small x is the image points, okay, corresponding to these x, right? So what we are trying to do is, as I said earlier, we know which are the 3D points which we have chosen here, and using some image processing or computer vision techniques, I have found out which are the correspondence points over here. And what we are trying to do is we are trying to calculate what is the camera parameter from this, given these two information, right? So let's say you have solved this and you have found out an estimate for P. So let me call it as P cap, okay? And it is, and you have found out an estimate of the camera, calibration parameters. Now, once we have this, what we can do is we can back project this. So once we have this P cap, we can just take this X and we can, back project it in order to find out what are the what are the values. I'll just put it as x dash over here, right? What are the projected values? So if I'm trying to project this back, okay, and trying to find out x dash, okay, I can plot this x dash over here along these. Now what I need is, when I'm trying to project back and find this x dash, if it is a perfect, if that particular p cap that I have found is exactly equal to p, or the actual camera calibration parameters, then that means this x dash and x should be coinciding. Okay, so we should get it at the exact same locations throughout. But if we see that x dash is not exactly coinciding and it is somewhat somewhere just near to x, then that means the camera parameters is not right, and that has to be recalculated or re-estimated to get a better estimate. So according to the optimization problem, what we do is, given this x and x, capital X, I try to find out an estimate for P, which is the camera calibration parameters, and then I back project that, okay, in such a way that I can find out what is the corresponding points in the image, and I try to find out what is the difference between these two images, okay, or I try to calculate what is the error function. Now once I have the error function, I use that to refine the estimate of the camera calibration, and this goes on, and like that slowly it becomes an it becomes optimized, and you find that it would somewhat coincide, or it would lie as close as possible to the actual correspondence image coordinates. Okay, this is again the same example which shows that, and if I calculate the root mean squared error over here, in this particular example it is 0.96 pixel for this particular image. So if you observe this clearly, what we'll see is, inside all of these small circles you have cross points, okay? So these small circles determine what is the actual position or what is the actual coordinates of the image point, the correspondence image points. And the small x that you see is which are present inside each of these is the projected image points. So our aim is to see that these projected image points coincides with the actual image points, and until that happens, or until that particular error function is minimized, to keep on iteratively finding out a better estimate of the camera calibration parameters. Okay. Now, another fact that may creep in when we are trying to take an image is called as a radial distortion. Okay. So, for example, an example of a radial distortion is shown over here. Like, for example, if you have this particular lab, we know that this is a table and it is supposed to be in a straight line over here, right? But we see that in the image we kind of get a curved image as shown, or a curved surface or line as you see here. Or if you look at here, this particular light, okay, what we see is that we know it is a light in the ceiling and it's supposed to be a rectangular kind of shape, but because of the radial distortion we see that it kind of gets a curved shape. Okay, so this kind of a distortion where you have, okay, this kind of this is the actual shape, or let's say if you have a square or a rectangle, it kind of gets a curved figure, right? So that's why you call it as a radial distortion, and that is one type of aberration, okay, that may result from the lenses, the camera lenses. Okay, and it depends on what is the distance separating the optical axis from the point of interest also. Like for example, here this is an image with a short focal length, whereas here there is a radial distortion with a long focal length, but which is not that much visible, so it becomes more visible with the short focal lengths. Now, when you have, so since you have these radial distortion coefficients, what we need to do is we need to ensure that when you're trying to calibrate the parameter, the camera, and when you're trying to find out the parameters, we need to ensure that the radial distortion is also taken into. So for that, what we do is instead of just using the camera, calibration parameter, let's say M, according to this formula, the small p stands for the image point, capital P stands for the actual image point, okay, not image, the actual 3D point, and this capital M is basically the camera calibration parameter. Okay, so along with that, you also have other terms here. Basically, it's the lambda that controls. So lambda means, lambda is actually a polynomial function which is determined from the normalized image coordinates. Okay, so what we do is we take a distance measure of the different points in the normalized image coordinates. Okay, and from that we calculate the polynomial here, lambda. Okay, and so what this basically means is we try to incorporate the information of the radial distortion coefficients also, and we calculate the camera calibration parameters. Okay, so if we are taking the radial distortion also into consideration, what happens is when you are, when you zoom in and compare with the previous image, you will see that this image gives much better results, where the actual projected image pairs will show, will coincide perfectly with that of the actual coordinates. Okay, so that is importance, or that is the importance of taking care of the radial distortion. So radial distortion is one kind of aberration that happens with the lenses and which needs to be incorporated while you're trying to calibrate your camera. Okay. So we were discussing about how we can calibrate the camera parameters, and before that we were discussing about how the 3D reconstruction is done with the stereo images. So the different steps in the stereo images is that first, given the fact that we know the camera parameters, how do you then find the correspondence points, and finally how do you back project that in order to get the 3D points. That was what we were discussing in the previous class and this class. So in the previous class, we discussed about the fusion techniques and the reconstruction techniques. And in this class, we saw how we can find out the camera parameters with respect to a calibration rig if the camera parameters are not known to us, right? Now what we'll see is that let's say the camera parameters, let's say it is not known to us, or let's say that it is changing constantly. It's not fixed throughout the image acquisition period, and let's say it is changing. So in that case, what we can do is this camera parameters, that is PQ, or let's say PP dash, okay, however we consider it, whatever notation we are giving. Let's say that we are finding these along with capital X, okay, that is the 3D point. That means in the reconstruction technique, okay, along with calculating the 3D points, we are also calculating the camera calibration parameters, okay. So we can put such a condition over here, right? So what we are trying to do, or in the method that we are trying to learn right now, what we are trying to do is we are trying to, each time we are calculating the 3D point, we also, just before that, we also calculate the camera calibration parameters, and then we proceed to finding the 3D point, and this goes on, right? So given a set of image correspondences, let's say the correspond, that means in the left image, if you have xi, and correspondence point in the right image, let's say is xi dash, right? And we know the correspondence between these 2 points. What we need to find out is basically the 3D point capital X or capital XI is what you need to find out, right? So in order to find out this, let's say, and you need the camera parameters for that, and let's say these camera parameters are not known to us, then our problem becomes it becomes the task of finding these camera parameters P, P dash, and Xi, right? Now let's see how we can try to find that out. So when we are trying to reconstruct, okay, along with this camera parameters, we see that we make use of the fundamental metrics. So if you remember, we had learned about the fundamental metrics and the essential metrics when we were learning about the epipolar geometry, right? So we make use of these matrices in order to calculate the camera parameters each time, because the fundamental metrics basically has the camera parameter information also along with that. So we can try to reconstruct using the fundamental metrics, but what we see is that it is only reconstructed up to a projective ambiguity. Okay, we'll see what that means later. Now we have the uncalibrated approach as well as calibrated. So when I say calibrated camera, what I mean is that the internal parameters are known to us, the external may or may not be known to us. And uncalibrated means both the intrinsic as well as extrinsic parameters of the camera is not known to us. Okay. So now what we do over here is, in this kind of reconstruction, as I said, we also compute the camera calibration parameters along with finding the 3D points, or along with determining the 3D points, right? So what we do is we make use of the fundamental metrics. So given the point correspondences, so let's say the points that we are considering is x and x dash over here. So if these are the point pair correspondences, then from this we try to first calculate the fundamental matrix, which is given by capital F. Okay. So from this capital F, after we try to find out, or after we find out this capital F, from this we can find out what is the camera parameters, because as I said earlier, the fundamental matrix, okay, basically contains the camera parameters also. So from that we can calculate the camera parameters, and once that is known, then we can find out capital X, which is the 3D point. So this is how the different the step-by-step approach, that is first the correspondence, then finding the fundamental metrics and the camera parameters, and then finding out what is the exact 3D point. Okay, and if the camera is calibrated, so calibrated in the sense you know the intrinsic parameters, okay, you may or may not know the extrinsic parameters, but if you know the intrinsic parameters, then you can instead of finding the fundamental metrics, you just need to find out the essential metrics alone. Okay. Now for computation of the fundamental metrics, what we do is, so how we start off with is, what we know is we have this point to point pair correspondence, right? That means in the left image, if I have a point x, and in the right image, I have found out what is the correspondence point, which is x dash. So if this point to point correspondence is known to us, then what we do is we try to find out the fundamental metrics. How we find out is by using this formula. I take x dash fx is equal to 0, right? And this one I can consider for all variables over here I, right? So for each of the point pairs, where I is a row over here, for each of the point pairs I can find out what is x dash fx, fx is equal to 0. So by implementing this formula, since I know x dash and since I know x, okay, and if I calculate for all i's, what I get would be again a system of linear equations, and from that I can easily calculate what is capital F, right? And capital F, once I know capital F, then from that I can find out what is the camera parameters. And then after that, I can find out the camera parameters. That is, I can find out what is P and P dash. Let's say P and P dash are the camera parameters. So how do I find that out? So what I do is I take one of the camera, metrics, or camera, projection metrics. I keep one of those metrics as the reference. So let's say I write it as I0, okay? And with respect to that, I try to, calculate for P dash, that is for the second camera projection matrix. And you can easily find that out using this particular formula. So what I can do is I can simply take the cross product over here, okay? So here the E dash is basically for the epipolar poles that you see, right? And I just find out what is the cross product of those epipolar points with that of the fundamental metrics in order to get the camera metrics for the second camera. Okay, so once we know this P and P dash, that means we know the camera parameters, right? Then we proceed as usual. We go with the actual method of reconstruction, okay, wherein, so once we know this x, we know this x dash, and we know what are these camera parameters over here, I can simply project it using the pinhole projection model. I can simply project both of these lines over here, and I can look at what is the line of point of intersection of the two lines, and that point of intersection would give me capital X, which is basically the 3D point. Okay, so, and this is something which you have already learned earlier. Now, in this case, it will work for all the points which are present in the epipolar plane. Now, you need to remember one point, that is, any two lines in a 3D space may or may not intersect. Okay, so you cannot expect two lines to intersect, any two lines to intersect in a 3D space. So what we do here is, we make use of the epipolar constraint, where we say that now this 3D point lies along the epipolar plane, right? And anywhere within the epipolar plane, by using this pinhole, camera projection model, we can try to reconstruct by just projecting these rays and finding out the point of intersection. But that can be found for any points except for the baseline. That means, let's say if I'm considering the 3D point to lie along this baseline, that is somewhere over here, then in that case, this particular method, triangulation method, will not work. Okay, because then if this is the point, if this is the 3D point, then the corresponding image point would be here. Okay, which is nothing but the intersection of the image plane with that of the baseline, which gives me the epipole. Again, here also I get this image as E dash. So that means if I have any point on the along the baseline, then its image I will get in in the left image as well as the right image as the epipoles. Okay, so because of that, what I do is, now just like before, if I'm trying to just project this, right, then that means it can lie anywhere along the baseline, right? So same way here also, if I try to project this, it can lie anywhere along the baseline. So because both of these are exactly coinciding with each other, these rays that I'm trying to project, so it's called as back projected rays. Okay, so the rays that I'm trying to project coincides exactly with each other, and because of that, there is no triangulation that is happening, right? It is lying along the same two lines, and therefore you cannot find out that point. You cannot find out that exact point. Okay, so except for the 3D point lying along the baseline, anywhere else if it is lying along the epipolar plane, then by using this triangulation method or the camera projection model method, where you try to extend this particular line, that is the line joining the camera center with that of the image, we can find out what is the 3D point. Okay. Now, another point which is important is the reconstruction ambiguity. Okay, so what reconstruction ambiguity means is, so we have learned the different steps by which you can reconstruct a particular scene using the stereo vision or the stereo images, right? And reconstruction ambiguity means that after you have reconstructed a particular scene, reconstructing means basically you're trying to find out what are the 3D coordinates of the actual 3D points in the world coordinate frame, right? So when you're doing such a reconstruction, there are some ambiguities that may be present. Okay, one such ambiguity is the placement with respect to the 3D coordinate frame. Okay, where exactly is the position? Okay, or what exactly is the orientation of a particular scene? Okay, those are some things which are ambiguous to us. Like as an example, we cannot say what is the exact latitude and longitude of a particular scene that we have reconstructed. Okay, or I cannot say, if let's say there is some kind of a corridor, okay, or something that is directional, I cannot say what is the exact direction. Is it north south, or is it east west, or so on? Okay, so this kind of a position and ambiguity in the position of the particular scene that has been reconstructed, as well as the orientation of the scene that has been reconstructed, is there, right? So that is one kind of reconstruction ambiguity. Okay, so because the position and the orientation does not, we do not have a clear idea of that, what we can say is, you can say that the scene is reconstructed, okay, up to a Euclidean transformation with respect to the world frame. Okay, that means if I take the world frame, okay, I have reconstructed a particular scene, but that reconstructed scene, okay, if I since I cannot say what is the exact position in terms of the world coordinate, that is, for example, latitude and longitude, right? Or I cannot say the exact orientation of the particular scene with respect to the actual world coordinate. In that case, what I can say is, at least what I know is, this is some kind of a Euclidean transformation of the actual case. Okay, so that means if I take the actual case, and or if I take the reconstructed in a 3D scene, and if I do either a rotation or translation, or a combination of rotation and translation, then I can get the actual reconstructed 3D scene within the world coordinate. Okay, so that is one reconstruction ambiguity, where you say that the reconstructed scene is up to a Euclidean transformation with respect to the world frame, and that means if I apply a rotation and a translation to that particular scene, reconstructed scene, then it is definitely we can we can find out, or we can say that it is a Euclidean transformed image, okay, of the world, I mean, with respect to the world coordinate system. What I'm trying to say is, let's say if this is a world coordinate system and this was the actual scene that we were trying to do, okay, we must have got an image like this. Okay, so it is reconstructed perfectly, but it may be a translated or a rotated version with respect to the actual world coordinate. That's all. Now, another reconstruction ambiguity that we can have is with respect to what is the actual size of this reconstructed scene with respect to the image, world coordinate frame again. So if I'm taking the world coordinate frame, okay, and if I'm reconstructing a scene, okay, how exactly is it now? Is the scene this big, or is the scene this big, or so on? Okay, trying to find out what exactly is the size of the different objects in the image, or what is exactly the scale of the image would be another reconstruction ambiguity. Okay, so that kind of ambiguity can be, you can say that it is equivalent to having a transformation, a scaling transformation. Okay, so from the Euclidean, you can say, if you're also considering the overall scale, okay, of the image, then I can say that, okay, it is up to, we can reconstruct it up to a similarity transformation. It's no longer a Euclidean transformation, but because you have also the scaling factor, then you can say that it is, you can reconstruct it up to a similarity transformation. Okay, so what we've discussed in today's class is, we started off with the smoothness constraint, where we said that in the disparity map, we try to find out, or we try to impose the smoothness constraint in order to reduce the noise which is present there, right? And what we learned after that is, how do you find out the camera calibration parameters? And then finally, we discuss about certain ambiguities in the reconstruction. Is there a doubt, anyone? Okay. Okay, so we can stop here for today's class. If any of you have any doubts, I can take that now. Okay, I take it that you do not have any doubts. So what we'll do now is, we have quiz. We have the